Exoskeletons are robotic devices developed to aid recovery after physical injury and to augment human strength and endurance. One of the core technologies behind today's exoskeletons are compliant actuators. These include the series elastic actuator and the variable stiffness actuator. Both are said to provide force augmentation to their human users in that they provide the mechanical work required for a given task. This often requires a sturdy structure and a large external energy source. Hence, these devices which aim to augment the human often constrains the human's autonomy. Humans rely on antagonistic muscles to generate both force and joint stiffness. It is metabolically expensive to generate stiffness. However, this is not the case through artificial means. There are mechanisms that are able to output a range of stiffness efficiently or using low power. This hints that it may be possible to develop a portable device to complement biological joint stiffness modulation, hence reducing the co-activation of antagonistic muscles and the associated metabolic energy costs. Following this idea, we present the portable Stiffness Modulator, a novel compliant actuator dedicated to human augmentation. The energetically autonomous device is able to provide intrinsically low-powered stiffness modulation without deliberately doing any mechanical work. This is thanks to the variable length torsional leaf spring design that it's based on. Using a motorized slider, output stiffness is varied by changing the effective length of the leaf spring. This design also allows the device to have other beneficial features, such as an infinite stiffness range and a constant motor force experienced by the motor during stiffness modulation. The mechanical simplicity and low-power nature of this design enabled the device to be compact, lightweight, and self-contained. The device was mounted onto a post-operative knee brace to test its human augmentation capability. A healthy test subject wore the exoskeleton and was tasked to perform a natural sit-to-stand-to-sit task. During the task, the exoskeleton stiffness was kept constant and the EMGs for the quadriceps and hamstrings were recorded. We use EMGs as a surrogate for the metabolic energy required by the subject to perform the task. The exoskeleton stiffness was then increased gradually for each subsequent experiment. These are the results of our pilot study. It shows that there exists a roughly quadratic relationship between the average EMG activation and the stiffness of the exoskeleton. At optimal settings, a 17.5% reduction in average EMG was recorded. This shows that stiffness augmentation is able to outweigh the effects of weight and other interfacing issues from the exoskeleton. Lastly, the power draw of the device was less than 2 watts during operation. In summary, this comes to show that it's possible to use stiffness modulation as a portable means of actuation for human augmentation. The proposed device may be useful in providing assistance in daily activities as well as rehabilitative purposes. However, it's worth noting that it may not be effective in supporting paralyzed patients due to its minimalistic design. Future work involves the improvement of the design as well as investigating the underlying biomechanical effects in greater detail. We have come to the end of the video. Thank you.